Imagine designing a battery that never degrades, or a highly targeted medicine to treat a specific disease, all without ever touching a chemical in a lab. Scientists call this in silico design, the ability to build and test new materials entirely within a virtual world. To make that virtual world real, researchers have to solve a massive mathematical challenge, a formula called the Schrödinger equation. You can think of this as the master rulebook for the universe's smallest inhabitants, the electrons. Solving this math is vital because these electrons are what hold atoms together. If we can predict how they'll move, we can predict exactly how a new molecule will behave before we ever try to manufacture it. Mastering this equation is the shortcut we've been looking for. It allows us to move straight to the solution instead of spending years on physical experiments that might not even work. To understand why this is so hard to solve, picture those electrons not as simple points, but as a huge, synchronized group of dancers performing a wildly complex routine. For a long time, the only way to solve the equation was to try and write down every single potential step and interaction for every individual dancer in a massive, impossible-to-read manual. Tracking the interaction between two dancers is simple, but as the group grows to 80, their influence explodes into the billions. This data explosion creates a mathematical wall. Calculations become so heavy that powerful supercomputers freeze, unable to handle the volume. To keep making scientific progress, we can't just keep building bigger computers to track every single footstep. We need a way to understand the dance without getting lost in the individual movements. This is where the strategy changes. Instead of manually calculating every interaction, scientists are using artificial intelligence to watch the entire molecular dance and learn the group's underlying rhythm on its own. But to get it right, the AI has to learn a very specific physical rule that electrons always follow, the Pauli exclusion principle. You can think of electrons as absolute divas who refuse to do the exact same move. If two of our dancers happen to swap positions, the entire routine has to perfectly mirror flip to stay in balance. Recently, researchers built new AI models that are designed to understand this mirror flip rule from the very beginning. Because they know the rule, they can find the right answer with incredibly high accuracy without needing to crunch every single individual number. By teaching AI the basic rules of the dance, we can finally predict how complex chemicals will act with a tiny fraction of the effort it used to take. Even so, when a molecule gets really large, the number of dancers is so high that even a smart AI can start to lose track of the choreography. To solve this, scientists borrowed a piece of technology used in modern AI language models, something called a transformer. When you use an AI to write a text, it uses a mechanism called attention to figure out which specific words are the most important for the meaning of a sentence. Chemistry researchers are now doing the same thing. This attention mechanism works like a spotlight. Instead of looking at every single electron at once, the AI focuses only on the specific groups that are interacting the most intensely in that exact moment. Combining the logic of language models with quantum physics gives us a much smarter way to view the dance. It lets us see the complex relationships that traditional math was never able to handle. This is now becoming a standard 3-step playbook for scientists. Step 1 is setting the stage. The researcher tells the software which atoms they want to work with. Step 2 is training the network. The AI analyzes those atoms over and over until it discovers their unique, stable electron dance. Step 3 is extracting the blueprint. Once the AI understands the movement, the scientist can accurately predict how that molecule will behave in the real world. This process turns deep physics into a practical engineering tool, bypassing the data jams that used to stop research in its tracks. We are moving away from an era of guessing with brute force math toward an era of recognizing patterns. When we can accurately simulate a molecule's behavior on a screen, we don't have to spend years physically building and testing thousands of versions that don't work. We can identify the single winner digitally first, cutting out years of wasted lab work. These models allow us to perfect a design before a scientist ever picks up a pipette, ensuring that when we do go into the lab, we already have the right answer. Next time you see an AI write an email or answer a question, remember that the same underlying technology is also busy mapping out the invisible interactions that make our physical world work.